Welcome back, learners. We will continue our journey in the field of computational process design. So, interestingly, now we will shift our gears. In the previous cases, we have learned about uh, optimization based design, tabular design of heat exchangers, and so on and so forth. Now, we will see one more aspect of such design where we try to bring in the effect of sustainability in design. So, the coming 3-4 classes or maybe 4-5 classes, uh, we will speak about how to include sustainability as one of the key parameter in the process designs. Okay, so before we get started, just recollect the textbooks that we were looking into. The current topics would be mostly delivered from the reference 5, which is one of the classic textbook for sustainable engineering. It is by Professor Bhavik Bakshi, Sustainable Engineering Principles and Practice. Okay, and to some extent from the book by Professor El Halwagi on sustainable design through process integration. Our majority of the content is mostly coming from Professor Bhavik Bakshi's textbook on sustainable engineering, which is Principles and Practice, which is one of the classic textbook for looking at sustainability as a metric for design. So, we can do a quick recap. So, we have started our journey with learning the heat transfer mode. We learned that there are multiple heat transfer, for instance, conduction through solid material, okay, convection through solid surfaces with the help of a moving fluid, and radiation as electromagnetic waves. Then we learned about heat exchanger basics. So, heat exchangers transfer are the equipment that is used for efficient transfer of heat between two processes. So, they use heat duty, temperature differences, and heat transfer coefficients. Then we talked about from one heat exchanger to heat exchanger base networks. Then we talk about how to concurrently design networks that involve process streams based on heat capacity and temperature differences. And we learned an important concept of composite curve and visualized heat demand of supply getting heat recovery opportunities. Then we have looked at problem table algorithm. If you want to summarize, so in the problem table algorithm, we looked at heat exchanger design by means of target calculation. We also broken down the process by means of temperature intervals and done the heat balance and found to optimize the energy efficiency. So, from heat exchanger, then we move to the reactor sizing, where we have done about proper sizing of the reactors, especially PFR, which is plug flow reactor, CSTR, which is stir tank reactor, for optimal reaction kinetics and conversion. Then we also talked about recycle reactor. Okay. Then we also talked about a concept of attainable region in what is and geometric. How do you geometrically compute that using reactor sizing? So, if we recall, the other topics that we have learned is heat exchanger optimization, that by means of heat exchanger network design by optimization. Okay. So, to minimize, so a typical heat exchanger network will minimize the energy cost by meeting the process requirement. So, if you want to minimize the heat utility or minimize the number of units adhering to the process constraints, whatever we want to for efficient operation. So, afterwards, we found that operability and the design are not two integral are not two different parts. They are integrally joined together. So, just not the design, but also the operation is also important. And for in that context, we talked about how to schedule a process by to maximize the production efficiency and minimize the downtime. So, this is typically done by sequencing the operation and identify the time intervals or the time points wherein you have to switch from one operation to another. Then further we talked about proactive and reactive strategies of scheduling. Also, we talked about a concept called preventive scheduling in response to various disruptions to achieve smooth plant operations. So, this was the contents that we have already covered. So, what we have to see here is none of them we were, so we were our intentions were highly objective. I need to maximize the profit. I need to maximize the number of units. Okay. So, see, when we want to look the world, so world is not an isolated island. So, we also need to look about what is happening. If something that if you do something, how it happens to your the if how it reflects on others. So, sustainability is something that a concept that takes care about that. So, when when you talk about yourself, you really don't. So, it's about your well-being, but it's not. So, you should yours whatever you do for yourself, it should also helpful to others, and by especially meaning it should not hurt others. So, for instance, you make a process plant here and it start emitting emissions, and it should not affect your nearby community. So, so you will for such an analysis, we will have to actually go across the design boundaries. We of course we have to study the individual processes, but we will have to look for how it is going across the boundaries. So, and your ideally your system, your design, your process design, it should be inclusive of that component. How do you achieve this concept holistically? The concept of sustainability comes from that perspective. Okay. So, now in this particular lecture, we try to quantify sustainability. Okay. So, we will try to quantify the sustainability for design, and we will see how this ideas, so how sustainability related ideas is useful for process design. Okay. So, the remaining part of this lecture, we talk about how to quantify. So, see, it is easy to say it should your action should not hurt others, or your emissions, the process plant that you have erected, its emission should not be affecting your nearby communities. These are all qualitative statements. So, in designers or even engineering, it's in itself is a highly quantitative process. So, how to quantify this actions and its repercussions, and how to quantify the sustainability. So, if you quantify the sustainability, okay, then we can easily include them into the design process, so that a trade-off can be achieved. So, in connection with that, okay, so we are going to now in this lecture, we are going to we are in fact trying to quantify what is sustainability. So, we will start with the basis of human building. So, the first part of this lecture would be fairly general, then we will try to make some of this concept quantify, and maybe in the subsequent lectures we will see how this can be included in the design calculations. So, achieving human well-being is just not about yourself. You have to integrate metrics such as GDP, which is the gross domestic product, human development index, and ecosystem evaluation tools into policymakers while decision making. So, we'll talk about each of this now. What is GDP? So, by considering multiple dimensions of well-being and their interdependencies, policy makers can develop effective strategies to promote sustainable development and enhance overall welfare of the society. So, there are multiple conflicting objectives. You have to make every country or every society would like to maximize the gross domestic product, and of course every human should achieve the maximum development, which is kind of quantified through the concept of human development index, and also it should not affect your ecosystems or the nature. So, we need to take all these together while deciding or designing anything. So, what is GDP? GDP is a measure of the economic output of a country. Typically, it is evaluated on country basis, sometimes state basis. But what is the problem with GDP? It's an economic output, but it's failed to account for the aspects of human well-being beyond monetary value. You actually monetized everything. Okay, so you talked about GDP is really good, and it just talks about human. It's just talked about the economic output, and it's all monetized human economic output. But what about the conditions that is beyond the monetary value? So while GDP is often used as a proxy for societal progress, it does not consider the factors as income distribution, environmental sustainability, and or the overall quality of life. So see, a country may be having high GDP, but it may be destroying the entire natural resources. Still, it would be showing that they would have the highest GDP. But is a natural way of progressing? So you kind of uh, destruct the entire resources and nature, and still you can have high GDP. That's why it is not a uh, it's not a representative metric. So if you look at the other side, so human development index, human development index slightly more comprehensive. Okay, why it talks about issues such as life expectancy, education, and income, and so on and so forth. So unlike GDP, HDI is a better metric, and it offers insight to the overall development and welfare of a population, reflecting broader spectrum of societal progress. So you are not only talking about something economic. Yes, economy is involved, but you are also talking things beyond that. So what are the triple values? Okay, so you need to have economically improved society, and socially just society, and environmentally benign society. So economic, social, and environmental consideration are typically useful in decision making. So a standard decision making process will mostly look only the facts such as economics. So there are things beyond which that impacts the society around you and also the environment around you. So sustainability is overall talks about how to integrate all of these things together. The triple values, how to integrate these triple values: economics, social, and environmental. By balancing economic prosperity with social equity and environmental sustainability, the sustainability approach would aims to enhance our human beings well-beings in a holistic manner. Okay, and acknowledging the interconnectedness. So economics is connected to the societal goals, which is also connected to the environmental effect. So all of them are connected, and it will form a circular chain, right? So one would have disturbance of one would have definitely impact on the other thing, and we need to have all of them to be placed uh, at a higher level. So we talk about now ecosystem goods and services. So there is some, so before we talk about the anything beyond the concept of sustainability, we'll have to speak about what we call it as ecosystem goods and services. So ecosystem goods and services, you have to quantify what is that ecosystem gives to you. Ecosystem goods and services are the services that uh, benefits the human from nature. So what are those? So there are three services. One is provisioning, other one is regulation and maintenance, and cultural services. What is provisioning services? Provisioning services are the products from the ecosystem, such as the food that we eat, water that we drink, and the material like wood or other building blocks and plants that you are getting from medicine, and so on and so forth. And you also get natural resources for industries like agriculture, fishing, forestry, and so on and so forth. This is what you provision from ecosystem, and regulation and maintenance services. The other one is how to nature kind of balance the earth climate by regulating or absorbing carbon dioxide and releasing oxygen through photosynthesis. They also regulate water cycle and also helps to store more water, which helps to, again, which helps to prevent floods and gives water during the drought time, and also provide habitats for a wide variety of plants, animals, and microorganisms, and by contributing and thereby contributing to biodiversity, which is the most important thing in for an ecosystem stability and also in terms of resilience. And if your ecosystem is good, it will also reflect the human health and well-being. So see, you over a period of time, let's say global warming has increased the temperature, okay, of the earth, that has effect, that had made uh, drastic effect in terms of natural disasters, and so on and so forth. So if the ecosystem is regular, and if the ecosystem is under, can regulate the environment around you, it actually gives good things to the human health and well-being. So you really want the regulation and maintenance services of the ecosystems to be active. Fine. And the third aspect what we are getting from the ecosystem, it is the cultural services. So it is non-material benefits. So in the first case, it was material benefits. The second case, it was a service that helps to regulate, and the third is cultural services. We enjoy ecosystem. For instance, we go for hiking, we go for camping, we go for wildlife watching, we might go out for a picnic, okay, and for which we all look for ecosystems. We are always going, we are always interested to go into the greenery, and it typically offers aesthetic and cultural benefits, and also inspire art, literature, and even spiritual connections as well. So what is the key aspect? So ecosystem is an important element in your human life. So humans are connected with society, and society is eventually ecosystems are around your society. So ecosystem services, which we quantify, which is provisioning services, regulation and maintenance services, or cultural services, they are not easily replaced by human made technologies. You cannot make uh, you may be possible technology, you may be able to make an artificial made forest, but that will not have the effect of the real forest. So ecosystem services are not easily replaced by the technologies and interventions. You can try to do some extent, but they are not like full replacement. So what is the current scenario? Overexploitation, habitat destruction, and pollution can degrade ecosystems, leading to the loss of biodiversity, decreased resilience, and potential harm to the human health and livelihood. So that is the current scenario, and we really want your ecosystems to goods ecosystems to behave well, so and continue to provide goods and services, so for the uh, well-being of human. So what are the status of this ecosystem goods and services? Okay, so various ecosystem goods and services have been degraded or used unsustainably due to the factors such as habitat destruction, pollution, overexploitation and natural resources, and even climate change. So for instance, food production. While the global food production has increased over a period of time, uh, there are concerns about the sustainability of current agricultural practices, including soil degradation, water depletion, and loss of biodiversity. So it seems to, you say that the global food production is increased, which is a indication of monetary benefit and therefore the indication of GDP. And what is happening? So your soil degradation is happening, water is depleting, and even there is a loss of biodiversity. Climate regulation. Ecosystems such as forest and wetland play a crucial role in regulating the Earth's climate by sequestering the carbon dioxide. So it absorbs carbon dioxide, and thereby the circulation of the carbon dioxide is lesser in the environment, and thereby reducing the temperature. So, however, the deforestation and land use change would continue to reduce the capacity of this ecosystem to mitigate this climate change. So, ecosystems are good in climate regulation, but what about? So see, if there are forests and wetlands available, they would do the climate regulation. But if there are not, what will you do after for that? And the third is water regulation. So, water regulation, okay, is about wetlands, rivers, and forests that regulate water, basically the flow of water in terms of quantity. But many of these ecosystems are now degraded, and dams and urbanization leading to water scarcity and water quality issue in many regions. So, ecosystem is a natural uh, has a natural capacity to regulate the water, but if there are the groundwater is depleted because there is no more water is because the soil is eroded, the water is not going inside the soil and just drains. So there is no groundwater, eventually leading to water scarcity and quality issues. And the last is all about biodiversity. So the global biodiversity continued to decline due to the habitat loss, invasive species, pollution, and other human-induced pressures. The loss of biodiversity is not only affect the ecosystem resilience but also affect the availability of resources for medicine and agriculture and other purposes. So, biodiversity is another quantity that has been severely affected due to the degradation of the environment. The ecosystem status and the status of the ecosystem goods and services typically vary significantly by region to region and also based on the ecosystem type. For example, coastal ecosystem would have coral reef and mangroves provide valuable services. Okay, and and so you can see that in many places. So this coral reefs and even mangroves are under most threatened species and thereby also affecting the ecosystem, the, the connecting ecosystem basically due to human activities. So the summary here is that of course there are goods and services ecosystem that provides to us, but over a period of time it has been become downgraded due to uh, various human activities. So now let us define what is sustainability. So with an increasing realization, what we with the increasing realization for the need to pursue sustainability, because eventually you need to match or you need to actually uh, preserve all of them. So you have multiple definitions of sustainability. So one such definition is sustainable development ensures that humanity meets the need of the present without compromising the ability of generations to meet their own needs. The second, sustainability is a possibility that human and other life will flourish on earth forever. And there are many such definitions possible. And what is the common characteristic of all this definition? So the one of the common characteristic is that the sustainability is anthropocentric. So it is basically uh, it's basically connected or primarily focusing upon human well-being, in contrast to our misunderstanding that you are always looking at the natural resources. So see, sustainability always talking about human by coexistence. So it is not the other way around. So sustainable development is about not only about the present and it's all about the future. It emphasizes of short and long aspects of satisfying human needs. And nature plays an essential role in sustaining human activities, and limits to such sustainability of human activities are imposed by the ability of the ecosystem to provide resources to and absorb impact. So there may be a boundary of the sustainability due to the human activities, which typically depending upon the ability of the ecosystem to provide resources and also to absorb the impact. So now that we have a qualitative definition of sustainability, can we do evaluate sustainability? So if you evaluate sustainability, see where we have come from. We started from a non-objective condition, like basis of the human well-being, and we identify that for the basis of the human well-being, one major component is ecosystem goods and services, and we say that ecosystem goods and services are typically now degrading, okay, and we need to restore all, and that would result in sustainability, okay. Sustainability definition itself is now qualitative, it's vague, you can't quantify. Now let's see how we can assess the sustainability, so that if the sustainability can be assessed, we shall be able to integrate them in the process design. The goods and services extracted by the human activities from the nature need to be quantified for the sustainability assessment. So, how much is the extraction from the nature of the goods and services? That information is needed for the sustainable assessment. Accounting for the capacity of the ecosystem to supply goods and services that are demanded is needed to satisfy the requirement of staying the nature's carrying capacity. And also sustainability requires the consideration of the process in a life cycle, all the way from the extraction to the consumption and again end of the life. So you have to look at how a product is being designed, manufactured, okay, used, and also reached its end of life and it coming back to its original form. So there often exists a trade-off on reducing the impact by reducing the type of impact, and what would eventually result is this might cause the other impact. For instance, what we have to see that this is a system that is spread across boundaries. So you sometimes reduce something that would have an impact on other things. For instance, let's say assuming that the uh, non-renewable fuels, for instance gasoline, etc., we use in IC engine and it results in emission, and suddenly we take a knee-jerk step saying that okay, they all increase emission, so to reduce emission let's start supplying the carbonaceous fuels. So what would happen immediately? Okay, so the emission production will come down as a result, which is good for environment, but your production capacity is also coming down. So you have to look at the assessment method should look at a holistic picture. Any step or impact that you do at one level would have an impact or an effect at another location. So you have to integrate them, all of them together. As a result, and this has become a cross-cutting across various disciplines, starting from engineering to environmental science to economy, sociology, and so on and so forth. And we also need to look for how these things are interconnected in their operation. So one way such to identify this interconnection. So we spoke about assessment and how to assess. Okay, so once you have to assess, you will have to actually go across roles, and once we start doing that, we find that they are all interconnected. So how to capture this interconnections? Okay, so that is what is being made available by means of this idea called life cycle networks. So life cycle networks are representation of interconnected processes and flows involved in the life cycle of the product, services, or system. Okay, so you have so when you talk about a product, for instance heat exchanger, and so we are planning to design heat exchanger, so we have to look for what all things are interconnected in that case, in the entire cycle of the product and the services that we provide or the system as a whole. To understand this life cycle on a simple basis, let's consider the case of of travel. So for achieve 1 kilometer mobility, you need fuel. So fuel, okay, and for fuel is you will fuel your car, okay, but fuel is coming from by transportation from the place of fuel refining, and from the fuel is reaching the fuel refined location from the point of extraction. So you see a chain of things happening, okay. And for mobility, fuel is only one of the components. So you will need to have car. For instance, if you have a car, and you have to talk about the manufacture of the car, and of course your travel would be smooth or not smooth, that depends upon the maintenance of the road, okay. Again, how to construct the road, there are material involved, okay. There are something you may have to do car maintenance that would require what we call it as the automotive repair, and there are certain regulations of the government, and that uh, controls certain aspects of it, and also the what you call the agencies like police control certain aspects of it, and most of them would have an impact on the healthcare, because the emissions that you provide will have an impact on the healthcare. So see, when you talk about a simple case of mobility of 1 kilometer, you see how many such things are interconnected. A standalone design, okay, a standalone design essentially so these are the energy flows, okay, and these are the other related activities. A standalone process will only look at mobility, but if you wanted to make this mobility sustainable, eventually you may have to look for this entire gamut, okay, but this which itself may not be complete. So how to represent such networks? This is what is being done by means of life cycle networks. So life cycle networks are representation of interconnected process or flows in the life cycle of the product, service or system. These networks visualize inputs, outputs and relations between different stages of their life cycle, facilitating analysis, optimization and sustainability improvement. So you need to have this entire gamut to be understood when we talk about at least when we talk about a simple case like emission. So how to assess the life cycle network? So again, we are going always one step ahead. We have to talk about sustainability, sustainable assessment of sustainability. Then we say that your sustainability is just not about something, but it's all about a group of things that is connected. Now we have to talk about evaluating 1 kilometer mobility. Is always, it's all about evaluating this entire scheme. Okay, this is typically done by means of life cycle networks. So for which, so you have to for assessing the life cycle network, there are 3 steps involved. You have to define the goal, definition, and the scope. If you don't define the goal or scope, this network can be infinitely huge. So you have to stop at some point. You have to reasonably stop at some point and identify the best way that you can represent this. And you need to identify what are the things involved and finding the data, which we call it as the inventory, and of course the last step is the impact assessment. Okay, so you need to identify the scope, identify the functional units, which are the basic unit in each step, and identify the data corresponding to it, and finally do the impact assessment. And eventually you have to interpret all of them together and identify there is an opportunity for improvement. So okay, so now when we speak about in goal definition, we speak about the functional unit. So what is a functional unit here? So when we speak about functional unit, a functional unit in LCA is a quantifiable measure that represents the performance of the functionality of a product or a system that is addressed. It serves as the reference unit for comparing different alternatives in the LCA study. The functional unit defines the basis upon which the inputs and outputs are measured throughout the life cycle, thereby allowing the meaningful comparison between different products or different systems. For instance, if if conducting LCA for paper production, the functional unit could be 1 ton of paper produced. So, this is one way of quantifying the functional unit. We are looking for 1 ton of paper product, for instance. So, this functional unit enables the comparison between different paper production processes in terms of their environmental impacts per ton of the product produced. So, and the steps involved include, of course, raw material extraction, manufacturing process, transportation, use and disposal. So, look at other certain examples. So, scenario, compare the environmental impact of two different types of light bulbs, for instance, incandescent lamp and LED bulbs. In the functional unit here could be a light a light bulb that can provide the 100 hours of illumination. So, LC input in this case includes the raw material extraction, manufacturing process, transportation and use of energy, and eventually dispose the product after their end of the life. And what would be the LCA output? Of course, we are basically looking for the components that what you call affects our system. This includes carbon dioxide emissions, other pollutants and energy consumptions. So, by using the functional unit of 1000 hours of illumination, we can compare the environmental impacts of both bulbs based on the life cycle assessment, taking account of the factors such as energy resource, energy efficiency, resource use and emissions for a specific functional unit. So, all our analysis would be based on a specific functional unit. So, let us see an example wherein we define this analysis, simple mass balance analysis, where we use the concept of functional unit. So, E10 fuel is made of 10% ethanol and 90% gasoline, while E85 fuel is made of 85% ethanol and 15% gasoline. E85 fuel allows a vehicle to travel 20% less distance per volume of the fuel compared to E10. This is because the ethanol has a lower value than gasoline and the engines running on these fuels are different. When comparing the life cycles of these fuels in otherwise identical vehicles, we want to know the amount of ethanol and gasoline in each vehicle would use for the selected functional unit if an E10 vehicle has a fuel economy of 15 km per hour. So, let us look at the case. So, E10 and E85 fuels for mobility. So, a distance of 100 kilometer travel with either fuel can be selected as the functional unit. This is how you define your functional unit. So, let's we can do the analysis for E10. For E10, the fuel economy is 15 km per hour. Hence, to travel 100 km, a vehicle would typically take 6.67 liters, and out of which is 10% is ethanol. So, 6.67 liter times 0.1 is 0.67 liters, and the remaining 90% is gasoline, which would be 6 liters. So, for E85, because E85 travels 20% less distance, its fuel economy is 80% of that of E10, which would result in 0.8 times 15 km per liter, which would be 12 km per liter. And to travel 100 kilometers, we would need 100 by 12 kilometers, which is 100 by 12, which is 8.83 liters, and out of which is 85% is ethanol. So, 0.8.33 into 0.85 is 7.08 liter. And the remaining 50% is gasoline, that would happen to be 15 liters. So, we have to understand this quantification of all of this was only possible since we have defined the functional unit. If we keep the functional unit term hanging, we may not be able to do any of this. So, once we define the functional unit, we can now talk about the network of the functional unit. So, there are multiple networks possible. One we call it as a process network. Okay, in process network, typically represented by means of presented like this. Okay, so here we are looking for life cycle strategies of a product or a system that are represented as interconnected processes, likely each transforming each input to an output. So, each unit here would transform an input to an output. The second type of network that we can use is input output network. So, input output network where the life cycles stages are represented as interlinked sectors. So, these are all sectors, and inside each sector uh, you have processes available. But you are only looking for each sector which inputs to the other sectors. So, only as a sectoral inputs are shown. One sector would give input to other sectors and consume the output from the others. And each interlinked sector produces the input for the others. And a hybrid network, which is like a combination of the process network and the input output network, as we see over here. Okay, so it combines the elements of both processes and input output networks to provide a comprehensive representation of the life cycle. So now we will see how such process network can be used, can be made uh, for a process. For instance, the process making of corn ethanol. So, ethanol manufacturing requires fermentation, and fermentation output would give you ethanol, and also you will have byproduct, which is the dried grain solid, and you require an equipment to that. You require an energy to do that by means of potentially natural gas, and there would be some water that is left over. An input to the fermentation is corn. See, but the corn has to be transported to the point of fermentation by means of some mechanism wherein you use some fuel and a device for mobility. Fine. And for the transportation, you need to get the corn from the farm. Okay. And for farming, you use many things. So you may use pesticide, fertilizer, and farm machinery would use equipment that requires diesel. And of course, there are part of the plant that other than the grain initially, and you also need to supply water. Okay, and water of course comes back to the system. But how do you typically get water? It typically by means of opening up a dam or something that would partially uses electricity, and it may you need to run the equipment. So it's all interconnected network. Okay, so now let us see how do we develop the network for uh, input output network for the corn ethanol. So we see that the ethanol manufacturing is right here, and you get ethanol and the byproduct, and that requires the feeding of corn, natural gas and equipment. And natural gas, you have a value chain for natural gas distribution, you have value chain for other industrial manufacturing, and you are sending in water, and corn is transported here by means of trucking, of freight trucking, and that requires certain petroleum resources, especially diesel, etc., for running your truck. And also you have to talk about the manufacturing the truck, because and corn typically coming from corn farming, that requires a lot of energy intensive production for equipment, fertilizer, pesticides, water. And water how comes in? So it comes from you need to do irrigation that requires some fossil fuel, and so on and so forth. So this is the entire input output unit. So you say that you are not looking at the steps, but you are only looking at the so you're only looking at the various stages in the network. So now how to do this hybrid network? So this is how to hybridize the network. You bring in the corn farming. Okay, and you say in the corn farming as a unit operation, you see that you bring all of them together, and eventually it becomes a hybrid network. And once we have such networks available, we want to do what is the type of analysis that we need to do. So are we looking a cradle to grave analysis or a cradle to gate analysis? Okay, cradle to grave analysis essentially means that we are evaluating the entire life cycle of the product from the material extraction, which we call it as cradle, to the end of life disposal, which we call it as the grave, including all stages of production, usage, consumption and disposal. So this is the most comprehensive assessment about the environmental impact associated with the product or a system uh, throughout its entire life cycle. It also enables us the consideration of all stages of the product life cycle, allowing the identification of environmental hotspots and opportunities for improvement. So, for instance, if you wanted to assess the environmental impact of a laptop computer from the extraction of raw materials, manufacturing, distribution, and of course, the energy consumption and end of the life disposal for recycling, landscaping, or incineration. So, what is cradle to gate analysis? Cradle to gate analysis include all stages of the cyclic steps of the product or system until it leaves the factory gate, excluding the use of the phase and excluding the use phase and the end of the life disposal. We stop our analysis when it leaves the factory gate. So here this focuses more on the impacts associated with manufacturing and the production, providing insights into the environmental performance on different manufacturing methods. And this is much more simpler. Why? Because you don't have to look for the end of the life calculation and thereby simplify the data collection and make it more manageable based on the analysis. So, for instance, evaluating the impact of a plastic bottle from the raw material extraction to the point of leaving the manufacturing facility, excluding the consideration of transportation, use, and disposal. For instance, certain methods may be useful in terms of cradle to gate analysis for its electricity production. So, electricity production, you may say that once the electricity is produced, you don't need to worry about how it is being used by um, uh, different people, different organization, etc. And you may stop our analysis the cradle to gate level. So once we are broadly we are progressively increasing our complexity. We talked about the sustainability, then we talked about a functional unit. From functional unit, we talked about networks. When we talk about life cycle networks, that include input output network, process network, hybrid networks. Now we have to fix the system boundary for analysis. So once the system boundary is fixed, we either use a cradle to grave boundary or cradle to gate boundary, then we can do the inventory calculations. So let's take an example. Consider the production of 1 kilogram steel. This process involves iron ore production, extraction, steel manufacturing, transportation of materials, and energy consumption. We want to calculate the environmental impact in terms of the carbon dioxide emission associated with producing 1 kilogram of steel. What is the step 1? You have to identify the process, list all process and its life cycle of steel production, including extraction, processing, steel manufacturing, transportation, and related energy consumption. Okay, in step 2, what you have to do? You have to gather the input and output of each process, that include raw material, energy inputs, process emissions, and waste outputs. And the step 3 is quantifying this. So, convert the data collected into standardized units. For example, raw material inputs. For instance, we wanted to specify something, let's say 500 kg of iron ore, 200 kg of coal, 100 kg of limestone. Okay, the energy inputs are 1000 kilowatt hour of electricity. Okay, 50 gigajoule of fuel, and what you have process constraints of 1 ton of CO2 emissions, and so on and so forth. So you quantify that. Then the next step is normalize the data. So the normalization is necessary. So we need to normalize the data to each functional unit. In this case, we wanted to calculate the environmental impact per kilogram of the steel produced. For example, normalize the energy input and emissions to kilogram of CO2 per kilogram of the steel produced. Calculate the emissions of the associated each input, CO2 emissions per kilowatt hour of electricity, and multiply by the corresponding process quantity. And finally, calculate the environmental impact of the entire cycle. This includes adding up the normalized emissions from all the process. For instance, to compute the total emissions of CO2 emissions from per kilogram of steel produced, you have to compute the CO2 emissions from iron ore extraction, CO2 emissions from steel manufacturing, CO2 emissions from transportation, and CO2 emissions from energy consumption. So there are 5 steps involved, and once we are done with that, we can compute the life cycle inventory calculations. Again, identify. So we'll show a couple of examples. Determine the total amount of benzene emitted in the extraction conversion of natural gas into 500 kilowatt hour of electricity. So identify the process. There are two things: extraction of the natural gas, when we call it as the process one, and the conversion of natural gas into electricity. Now collect the data. What is the kilogram of benzene emitted per 1 cubic meter of the natural gas phase extracted? Okay, what is the kilogram emitted benzene emitted per kilowatt hour of electricity produced? And again, what is the x kilogram of natural gas is unit for 1 kilowatt hour of electricity generation. Now quantify inputs and output. 1 kilogram, 1 kilowatt for 1 kilowatt electricity, natural gas extracted, benzene emissions. Okay, so corresponding benzene emissions. Okay, how do you do it? You multiply with the natural gas extracted times the value of the benzene the value of the kilogram of benzene emitted per 1 cubic meter, and you will get a number, and benzene emissions and corresponding electricity generated. Now they normalize the data into functional unit. In this case, the functional unit is 50 kilowatt hour of electricity. So you have to multiply with 15 in either cases, which would result in the results for this would result for the phase 1, and this would be the result of the phase 2, and calculate the total emissions. Okay, so total emissions per 15 kilowatt hour of electricity produced, benzene emissions uh, process 1, benzene emission process 2, wherein you sum it up, thus each of them together. So the result says that 7.96 times 10 power minus 4 kilogram benzene per 50 kilowatt hour electricity is used kilowatt electricity using the natural gas. So this is how you do the calculations. So now we look at one more interesting problem, that is connecting sustainability, which we call it as allocation problem. So what is the allocation problem? In allocation problem, it typically comes in LCA when multiple products or co-products are generated from the single processes or system, and it's necessary to distribute when it is necessary to distribute the environmental burdens. Allocation methods are used to determine how these burdens should be allocated among the products or co-products. There are three methods of allocation. One is partitioning, second is displacement, and the third is no allocation. So what we do in partitioning? In partitioning, the environmental burdens of the process are divided among its products or co-products based on their physical or economic relationship. This can involve allocating the burdens according to the mass, energy content, economic value, and other factors. And in displacement, this involves allocating the environmental burdens of a process to the main product or service while assuming that the co-products displace the equivalent products or services from the system boundary. For example, converting sugarcane to ethanol also produces bagasse, which is a commodity converted into electricity. So in this displacement based approach, the electricity from the bagasse is considered to displace the electricity from the conventional source that is obtained from that region, because let's say sugarcane actually absorbs CO2 when it grows, okay, and you use that when you make the electricity. So there is something that you may assume that some effect of the emissions are displaced because your process now uses a raw material that actually absorbs CO2. And the third is no allocation. So in the no allocation method, the environmental burdens of the process are not allocated to specific products or co-products. Instead, the burdens are accounted at the process level without further distribution. We just stop as it is, no partition, no displacement, we don't do any allocation. For example, let's say a solar energy drives a forest ecosystem, but the products and services by this system is entirely known, so you won't be able to either partition it or displace it. So let's look at an example. Consider a case of life cycle of process wherein A is fed into and result in P of 40 gram and 40 kilogram, and B is leading to a product Q and 20 to 100 kilogram, and eventually as part of this 120 kilogram of CO2 is emitted. This is the life cycle of a product and a byproduct Q. The product is interesting product is Q, and while the byproduct is interacting product is B, The byproduct is Q. And look at the life cycle of the process for producing Q alone. Okay, so only if you consider Q not as a byproduct, you say that it takes up an input and by means of an output it produces 2 kilograms of CO2, but it generates 2 kilogram of CO2, but for generating 1 kilogram of Q. So now we can allocate the CO2 emitted from the life cycle between these two products using partitioning, displacement and no allocation. So what is partitioning? In partitioning, we use the monetary value of the product to partition of the CO2 emission. The monetary value of the product is $20 as given and the byproduct is $200. So the proportion of the CO2 allocated to product P is the ratio of the value of that product by the total value. So XP in dollars, 20 by 20 plus 200 times 120 is the amount produced, will be 10.09 kilogram of CO2, while XQ would be 20 by 200 plus 200 divided by 20 plus 20 times 120, which is like 101 kilogram of CO2. So mass allocation you may be able to see that. Similarly, by means of mass allocation, this is of course by means of the ratio of the value. You can see that this is how the burdens are allocated, partitioned. And look at the displacement. So displacement, you can see that. So since while the Q is a byproduct, okay, and you are getting 200 kilogram of Q, but actual production of 2 would also result in some amount of CO2 emission, as we have seen in here. Okay, so for making 200 kilogram of Q, you are actually generating 400 kilogram of CO2. That's what written over here. But by making A, you are getting anyway a lot of Q as a result. So here you are actually generating 120 kilogram of CO2. Also, you have saved 400 kilogram of CO2 by generating 200 kilogram of Q. So the net displacement is 120 minus 400, which is minus 280 kilogram of CO2. And in no allocation, there is no allocation. You assume that this factor, the proportionality factor is 1. So XP is 120, X2 is 120. Okay, this is how you allocate the load. Now let's talk about the last topic in this session, the type of uncertainties in this an assessment. In LCA, there are multiple uncertainties that can occur due to various sources influencing the reliability and accuracy of the assessment. So you have to actually evaluate the uncertainty because of the various calculation that is involved. So there are 3 common type of uncertainties, which is parametric, scenario and model type. What is parametric uncertainty? Parametric uncertainty arises from the imprecision or variability in the input parameters in the LCA model. These parameters can include data on resource use, emissions, energy consumption and other factors. Scenario uncertainty, which stems from the uncertainties in defining the system boundary, selecting the functional unit and specifying the temporal and spatial aspects of the assessment. And model uncertainty, which refers to the uncertainties associated with the mathematical models, assumptions and simplification used to represent the complex system processor LCA. So either it can be parametric or scenario or model. And we have to understand this, how much is there in your analysis. By understanding and addressing these type of uncertainties and carrying out the sensitivity, the LCA practitioners can enhance the robustness and reliability in terms of the assessment, providing more insightful decision making for policy development. Just to summarize what you have learned, okay, this class was all about what is sustainability and how to quantify sustainability. Okay, so we started with what is sustainability assessment. It's about evaluating environmental, social and economic impact of products, process or systems to promote sustainable development and decision making. And we talked about a method to do that, which we call life cycle assessment. This analyzes the environmental impact of a product or a system across its entire life cycle from raw material extraction to the disposal, and there are various steps in LCA. You have to include goal and scope of the definition, inventory analysis, impact assessment, and protection of the results. And the functional unit, these represent the function or service provided by product or system, allowing the standard comparison in LCA. And types of life cycle network. We talk about process network, input output network, and a hybrid network with varying with varying levels of detail and scope. And last is all this analysis are, of course, could be affected by the uncertainty, which could be from the model, okay, scenario, or from parameter, thereby impacting the reliability and accuracy and assessment of the results. So in this upcoming classes, we use some of this concept and see how this can be integrated into a design framework, and so that an environmentally sustainable design could be achieved. Okay, with this, I think we will come to the end of this session. Thank you. See you in the next class. Bye.